Hi, Raj.
Hi Tommy, how are you?
Can you see me?
I can't see you. I can hear you, but not see you.
But it's probably the best option, really.
Right. How are you doing?
Fine, thanks. How are you?
Good, thanks.
Oh, brilliant. I'm the number. I'm for some reason I've been given a number.
Okay, no name, just a number.
4743. Yeah,
Oh, good stuff. Well, it's good that they can actually make it. I was wondering if they would or not, but it'll be good to catch up with them.
yeah. I think they are fairly accurate as to timing.
Yeah,
So um, you know, I mean, I hope half an hour. At least it's the second part of something you've already started. So it's
yeah,
not a completely new topic.
yeah. And I think
Yeah,
I'm going to do a little bit more about kind of working out what's going on with circuits, and then say if the students aren't getting it, then this is what we do.
yeah,
With that. So I'll do a little bit more kind of writing on the screen and a bit less
yeah,
going
yeah.
through slides today. So yeah, hopefully they get something out of it.
Um, I'll just see if I can. Just need to.
Oh, here they are.
Great.
Hey, yeah. Oh, fantastic. I can see somebody just in the background there. Hello. Oh, I'm not sure. I can't hear you. No, still can't hear you. Oh, something in the chat. Oh, no problem.
It's quite a good idea if you can be heard, if they can be heard, because then they can ask questions and all that.
And shout out and feel free to once we get the sound up and running, feel free to interrupt me. And the voice, obviously, this is a bespoke session for you guys. So if we end up on a tangent that's relevant to you, then that's completely cool as well.
Can you hear us now?
Yep, yep, loud
Oh,
and clear.
what did it? Oh well, it doesn't matter. Thank you.
Fantastic.
Oh, that was
Can you
you.
hear us this way?
Oh, don't worry, you
Or
won't
is
need
it,
to
is it
listen.
just on the computer?
Yeah, it's all right. Okay, lovely. Who else is coming then? I think we've got a smaller group this time.
Okay.
Yeah, yeah.
I think I'm off from that.
All right.
Oh, wait, now I can see it as well.
Oh, it's not come on the projector. I'm so sorry.
I love your wall display with the planets. That's really cool.
Oh, I can't claim it. I didn't do it. It was here when I came.
I was going to say, hopefully we can maybe once the exam groups are on study leave, I can pop in face to face as well.
Oh yeah, that'd be brilliant.
Face to face when we've all got a bit more time.
Yeah, yeah. Well, I don't think any more. Oh, where's Victoria?
Selena?
She's not in today.
Selena's not here.
No,
Is
she's
she
off sick.
Oh,
Yeah.
okay.
Okay, it's Fatosh. Hey, miss. Let me just. I haven't got a number. There's just one more. I think you can start. There's just one more person.
Fantastic. Shall we get going? Because I know
Yeah, because
you're.
the time is short. Yeah.
I
Yeah.
want to leave enough time at the end so that you guys can ask questions and whatever you need. So we talked before. My name's Raj. This is my introductory slide that you've already seen. So I'm a physics teacher at Dulwich College. I've also been head of physics and a head of science and academic lead for a group of schools. So I've always worked in and around London, and now I'm over in Dulwich in South London. So we had a chat previously about electricity, and I think I left you with these this little clip from TED Ed about the origins of all these words. But I was wondering, do you remember or can you recall what all of these terms mean? So units, terms, what can we say? So what's energy measured in?
Jules,
Shut up.
Jules, can you hear us?
Joules, yep.
Yeah.
So energy is measured in joules. Charge,
Coulombs,
coulombs, time,
seconds.
seconds. Yeah, and we may well need to do those conversions if the exam board gives us a value in minutes, then we need to times it by 60 to work it out in seconds. These lot here, these are kind of your core things. They're applicable across physics. So your kind of links between different subjects. So the students may have seen energy when you were studying things like energy and power and things like that. Again, charge, I would certainly draw links to chemistry when you're talking about charge. And again, time as well, kind of reminding students this is this universal thing. Then the two, we use an E for energy, a Q for the quantity of charge, and a lowercase t for time, with the uppercase T being used for temperature usually. And these are just conventions, but usually when exam boards ask you to give a definition of something, these are what they're expecting to see if the students aren't writing the words. Then we can move on to some electricity specific language, which is potential difference, measured in volts, and we use a V to represent it. And that is the energy carried per charge. And then we've also got current. It's completely cool to relate this to current, as in current in a stream or in a river or something like that, and use words like flow for current. We use the letter I. It used to be called electrical intensity, so that's why it's an I. And that's the rate of flow of charge. So how much charge passes a point in a certain time, and that's measured in amps or amperes. And then we've got resistance. We use the Greek letter omega, which is the last letter in the Greek alphabet. So students may have seen it, say, in church. They may see alpha and omega written there. So they may be familiar, they may have seen that symbol before. And resistance is our PD divided by our current. And then finally, power. And you can get to make that horrendous physics joke that we make every year and say, what is the unit of power? And the kids say watts, and you say, what is the unit of power? And you can go back and forth as long as your humor lasts for them. But power equals current times the potential difference in there. And so those are the relationships that you've got linking those first set of kind of universal values to those kind of core electricity terminology, core electricity values. And then we can go for those derived values, this resistance and power. And I think it's worth spending a bit of time at the start of the electricity topic, going through and saying, this is what we're working with. These are all the ingredients to the thing that we're going to end up with. So in terms of these things, how do we use them? There are three relationships or three laws that we can think about. Our first is Ohm's law. So usually written as voltage equals current times resistance. But it may also be worth spending a bit of time saying, okay, resistance is the voltage or the PD divided by the current. And current is equal to voltage divided by resistance in here. And this is a really nice picture that you can use. So current is the thing that flows. Current is the thing that's actually happening. Voltage is the push. And the resistance is is the thing that's stopping it flowing. So this diagram that I've got on the screen is quite useful for students to actually interpret what's going on there. So that PD, that potential difference, that difference in electrical potential energy, that's what's pushing that flow of electrons around the circuit. And your ohms, that's resistance, that's what's stopping it. And so if your resistance increases, your voltage is going to have to go up, your PD is going to have to push harder to get that same current. So with this relationship, once you've spent a bit of time having a look at this relationship, it's worth doing a bit of diagnostic questioning and working out if students can understand what's going on there. So a question like this is quite useful. Let you have a look at that. So we're looking at the current through different components. So she uses an ammeter to work it out, and she wants to find out which has got a bigger resistance. So we've got a buzzer here on the left, and then we've got a light bulb on the right. You've got two cells on the left and just one cell on the right, and then a reading on your ammeter. So you've got twice the push on the left and a certain reading on the ammeter, and just 1 times the push on the right. So you can ask students what's going on there. And this is a nice thing because we're changing this thing, and we're also changing the resistance. So we're changing two things, and we're saying, okay, what's the difference here? And we're doubling our voltage on the left compared to on the right, but we are more than doubling the current. So you can conclude that the resistance of buzzer A is lower than the resistance of the bulb B. That's quite a nice kind of diagnostic question to get students to explore. Then what we can do is get them to answer, explain it. So they may have got that previous one due to a misconception that just happened to be right. So it's quite nice to ask them to explain. And this is what we really want to see, something along the lines of there's a smaller current through bulb B. And that might be because there's only one battery. So if we double the amount of push, what are we expecting the current to do? It should double if the resistance is the same. But we don't get that, that idea. And it's okay to use this concept of saying, okay, the voltage is pushing it and it's a current that's flowing through. What I've seen some people do, which is quite nice, is for a homework, especially now that students are a bit more used to doing things online, is asking them to maybe record something on Teams or something like that with them, just with their voice explaining what's going on, explaining out loud, rather than getting them to do it in a written form initially. And that can be quite as to what those misconceptions are. I've also had seen some teachers use a simulation like the PhET simulation and ask students to talk them through what's going on and why. And that's quite a nice way of introducing these concepts. So we talked about there are three different relationships. Ohm's law. We now can talk about the relationships between current and voltage across a circuit. And it's worth actually having a look at networks in general. So this is a problem that if you've got quite a bright class, you might want to chuck with them. This is the problem called the Seven Bridges of Königsberg. And the problem that you've got there is you need to cross every one of those bridges once and only once. So you can ask students, maybe in a starter or something like that, to think about, can you think of a route which crosses all of those bridges once and only once? And actually, it's a trick question. It's not possible to do that. And that was proved by Euler, that it's not possible to make that. But it's a good way of having a look and saying, okay, can we think about how things are joined together, how things are joined together in a network, and how we can move from one point to another. Or you might want to talk about networks through something like the tube map as well. So you might want to bring the tube map in there and say, okay, right, I'm over in Regent's Park. I want to get to Monument. How do I do it? So if you've got maybe a lower ability class, you might want to just say, okay, what's the route? If you've got the slightly more able students, you might want to say, okay, right, these are the times between stops or something like that. How do we get the quickest route, and how can we compare the route? But we're still just playing around with networks and how things can flow and be joined together. Then we can introduce the rules of electrical networks. We can say, okay, right, we can think about systems and networks and how things flow from another, with a truck model, with water flowing around, with a bit of rope that's been passing around each other. But we're going to come to Kirchhoff's laws. And Kirchhoff has two laws. Kirchhoff's current law is that if you've got a node is just a fixed point, so just a blob. And I would encourage students to physically draw that blob on their circuit. Then we can talk about the current coming into the blob and the current coming out of the blob and say that they're going to be equal to each other. So if we add all the currents going into that blob and add all the currents coming out of that blob, they'll equal the same. We can also talk about this idea of a closed loop. You come out of the battery, you go all the way around your circuit and come back into the battery again. That's one closed loop. And the voltage we put in to the battery is going to be equal to all the voltages that are coming out of the battery. So with these relationships, we've got Kirchhoff's current law, Kirchhoff's voltage law, and then we've got Ohm's law as well. With these, we can solve most electrical problems. So let's have a look at this one. This is going to be Kirchhoff's current law. So we've said we put a blob in here, and we say the current going into that blob is equal to the current coming out of that blob. Get students to physically draw that current going into that blob. Those little arrows are quite useful as well. So we've got our current here. We know what it is. So that current's going to be coming around. Draw a couple of arrows. Maybe let's draw 3. And then we've got our blob here. So we know one of those arrows, one of the current is going to come down here. One is going to come down, 2 are going to come down here. And then we've got another node here. And we'll get this amount, Get this amount, this amount, this amount, this amount. We've got another blob, another node here. So those two currents are going to add together. And then, let's get those couple. This one, don't forget about this one. Let's bring them back. We've got another node, another blob here, so we're adding them up. And coming back, and we're starting off with the same amount that we've got here. So we can see that this amount here at the top is equal to this amount in A1. So this is going to be 0.270 amps. What they've done here is they've turned this into 27 milliamps. So we can turn that into amps, give a value in amps here. And what we can either do is we can think about these arrows adding up, or some students might prefer to write these values as essentially simultaneous equations or equations relating to these things. So with A2, we can say that we've got this value here and this value here. So we can say our 80 milliamps is equal to our value for A2 plus our 27. So then we can just solve for A2. And then for A3 here, we can say we've got our 0.270, which will be equal to our 80 milliamps. That's equal to 0.08 plus our value for A3. And if they write these relationships down, they can then work out what our values for A2 and A3 will be. Okay. So either it's worth spending time drawing those little arrows and seeing how those little arrows add up. These blobs, putting these blobs on to say, okay, this is where the current is splitting is quite useful. And then we can get the students in our exam to write these relationships and then solve for those relationships. So say, okay, A2 equals, A3 equals, and go on from there. I'm going to jump ahead and have a look at this. So now we've got our values for here. So we've got this concept of a closed loop. How many different ways are there of going out of the battery and coming along and going all the way around and going back in the battery? There's one. And then we've got our second one. We can go around this way and come back into the battery. And our third one, going around and coming back in the battery. So let's have a look at our first one. So we've got 24 volts going in our top branch. And if we're going to go around our first loop, we've got this 12 volts that we see first of all. Then we've got some unknown value. And then we've got our 2 volts that were coming through. And then we can solve for that value for V1. For our second loop, we've got 24 coming in. And we've got our value of the bulb coming in there. And we've got our second bulb. So we've got essentially those 2 bulbs are going to take the same value. Then we've got our 8 volts. Then we're going back through this original 2 volts. And then our final one going round through that bottom one, 24 is going to be equal to V3 plus that 2 volts. So we've got a list of equations there. And then we can ask our students just to rearrange and solve for those values. Okay. Hopefully, we cross our fingers. That's our first step. What would we do if students get those wrong? Depending on your students, you may find it's easier for them to actually physically build those circuits. Now, if we build them physically, often we can have problems with things not adding up because we've got a bit of resistance in the wire and things like that. So it's quite useful to actually get them to build the circuit in the simulation like PhET. And you may ask them to build a circuit from an exam question in PhET and have a go and see, okay, can you construct it? What happens? Let's take some measurements and solve it through PhET, and then describe what's going on in PhET, and then have a go at solving another exam question without that simulation. So that can be one thing we can solve. Again, that's for a parallel circuit. We've got that there. We can run through some diagnostic questions as well when we talk about, okay, we're adding a branch. I'm saying, okay, what is the value here? What's the value through a new branch? And so it can be useful for that. The other thing that can happen that students can raise is they can say, okay, right, when we're looking through our voltage, we're saying, where's our extra voltage coming from? Because if we add up V1 plus V2 plus 12 volts plus the 2 volts V3, it's going to come up to much, much more than 24. So we can go all the way back to our derived units and work out what our value is for power for all of those things. Because while we've got our voltage adding up to the number that's going to be larger than 24, our current is splitting at each of these nodes, each of these blobs that we can see. And if we work out our current for each of these things and work out our total power, then our power in watts will be equal to all the power of all of these different components added together. Okay. Let's whiz through. Right. I hope I've just done a real whistle-stop tour about how to answer some more tricky exam questions. So essentially, you've got Ohm's law, and then you've got Kirchhoff's voltage law and Kirchhoff's current law. We promised we'd finish by 5, but I'm happy to hang around for any questions that you've had or anything that you would ask me, how I would teach anything. Otherwise, I'd be really grateful if you can fill out this evaluation for Physics Partners on my behalf with that. So any questions, any kind of how to teach or anything like that that you've got for all these slightly more complicated electrical circuits?
Any questions?
I don't know if I can be heard from here.
Can you hear?
Yeah, I can hear you.
I'm just gonna speak louder.
Can you hear?
So
I can hear you.
you know the analysis, sorry, the explanation you gave about the extra power that needs to be pumped into parallel circuits. Do you think you could draw an analogy similar to what happens with different gears in a bicycle, or for example in a car, as in you reduce, you increase the gear, and then you get more runs per minute, but the power at the same time has increased? Do you think that could be an analogy, or would just end up confusing them?
So I've spent a lot of time kind of thinking about analogies and working with colleagues and things like that. And what I would say is that if your analogies can be really, really helpful. But what I would do is, if you're talking about analogies, I'm going to jump off of this QR code for a second. I would run a lesson in which you present more than one analogy. And then spend a bit of time talking about what those kind of strengths and weaknesses of those different analogies are. So I'd say, okay, let's talk about bicycle gears. And if you cycle to work, the students get really excited if you bring your bicycle into the lesson and chuck it on the, I don't know if your school is happy with that, but yeah, here's my bicycle and this is I can change the gears and so on and so forth. And then say, okay, and then with the bicycle, what's the voltage, what's the current, how does this analogy show that the current is not used up, the bicycle chain doesn't disappear, so that shows the current isn't used up. And we can swap it for different components by putting the resistance in there. But with the bicycle gearing, it's really hard. You can't split the chain, so you can't show parallel. But if we said, okay, the other one is we're going to do the Domino's pizza, where a couple of riders come out of Domino's Pizza, and one delivers pizza to this person's house, and then they come back, and then the rider is charge, and then they go down 2 different routes, and so on and so forth. Then that's got certain benefits as well, and it's quite nice to get students to evaluate those analogies. And compare them and say, okay, what about water? Now, physicists love to talk about water and plumbing and things like that. But actually, unless your students are doing a bit of vocation stuff around plumbing and that kind of stuff, then actually it's hard to get your head around plumbing. So you know, some of them they may say, oh yeah, I really understand plumbing because I was helping at home with sorting out the plumbing. Or they might say, I've got no idea how water flows. So yeah, I usually spend a whole lesson on misconceptions and analogies. And at the end, my plenary is around which analogy worked best for you. Different students say different answers. Sorry, that was a very long answer to your question.
That was a delightful answer. Thank you.
No worries. Is there anything else that you wanted to discuss? So I mean, my kind of 2 top tips, if I were to say anything, draw these little arrows, draw these blobs on your circuit. If the students have difficulty understanding it, run the sim and just get them to run the sim and say, okay, what's actually going on here? Because they want to build those mental models in their heads. Because actually these kind of diagrams, circuit diagrams, quite tricky to do. And I would run a sim rather than do it in real life as a practical, because you've got things like internal resistance of the wire, things like that. And then I know that you've got those core practicals that you have to do. I would do them afterwards once you've got that theoretical understanding of what's going on. And then when the students say, why didn't they add up? You say, well, you know, these wires, they've got a little bit of resistance in them and so on and so forth. Yeah, so put the arrows in, put the blobs in. If they don't understand, and if they struggle with the kind of linking between networks and tube stations or bridges or something like that, then run it as a simulation first and then do the practical side of things. Okay, thanks very much, guys. I don't want to keep you too long. I think we've just hit 5 o'clock.
Yeah, thank you very much.
No worries.
Thank you.
Thanks, and it'd be lovely if you can fill out that evaluation. That's really helpful for us.
How did we do that last time? Oh, did I send you the link? Yeah. Okay, I'll send the link.
And I think I'm under other. I don't think they've put my name on the drop-down list yet.
I'm going to do this. You scanned it. Oh, good. That's quicker because I'm still trying. I can't get I've put it onto minimum screen and I can't do cut and paste for the thingy bobby for your thing.
Shall I put it in the chat? Is that easier?
Yeah, that'd be fab. Thank you. I thought I could do it from there, but no, I'm half asleep also. That doesn't help.
There we go. It's in the
Thank
chat.
you. Thank you. I can work with that.
where does the difficult law, I think the rule on the margins. The difficult law can be derived by the original strategy. As much charge goes in, as much comes out. Fair enough. But we did them at 11.
And then you must let us know what if you'd like another session on something else. I know that energy is quite popular. People request it. Waves, teaching forces as well, tends to be quite popular as well. And then otherwise, hopefully we can maybe squeeze in something online between now and the exam period, and then once the students are away. I'm very happy to pop in when we've all got a bit more free time.
That'd be lovely.
All right, lovely. Well, I shall see you next time.
All right, thank you so much.
All right.
Bye.
Bye, guys.
Bye bye. Thank you. How do you spell your name? So sorry.
First name Raj, R-A-J.
Oh no, not you. Sorry.
Sorry.
I've got
That's
Raj,
all right.
Yeah. Sorry.
All right. Take care.
Thank you. Bye.
Bye.
How do you spell your name, sir? I've forgotten. How do you spell your name?
GI.
G-I, yeah. I looked for it